Number 13, an object with mass m is suspended from an elastic spring. With a spring constant k, the object oscillates with a period t. If the mass of oscillations is quadrupled, so we're quadrupling the mass, how will it change the period of oscillations? So period equals 2 pi square root microcores. And what we're doing here is we're quadrupling the mass. So 4 is underneath the radical sign. So the period equals square root 4, or the period has to be increased by a factor of 2. Number 14. An object with a mass m is suspended from an elastic spring, spring constant k. The object oscillates with a period t on the surface of the Earth. If it's moved to the surface of the moon, how will it change the period of oscillations? Acceleration on the moon is 1.6, or 1/6 meters per second squared, 1/6 what it is on Earth. So the period equals 2 pi square root microcores. So you can see that g is not a part of this equation, so the period is independent of g. So it's not going to affect this equation at all, so the period will remain the same. Number 15, a mass is suspended from a string, length L, undergoes simple harmonic motion, which is true about the period of oscillations. So now this is a pendulum, and period of the pendulum is period equals 2 pi square root L over G. And they want to know what's true. So let's see, A, the period increases with increasing amplitude. Well, amplitude's not part of this equation, so the period won't increase with amplitude. Period increases with increasing mass. Again, mass is not part of this equation, so the period's not going to be affected by mass. The period increases with increasing length. Length is part of that, so if we increase the length, we're going to increase the period. So that looks good. Whoops, not that one. Oh, that's wrong too. The period increases with increasing length, right? Because if we're increasing the length, that's an enumerator, we're going to increase the period. So D would be the correct answer.